So identifying absolute extrema on closed intervals is fairly straightforward. When we consider finding absolute extrema on other types of intervals, the process becomes a little bit more complicated. So the extreme value theorem that we introduced, that method of just identifying a few key points, plugging them all into the function, that's only going to work when we're looking at closed intervals. So if we're looking at open intervals or intervals that are only closed on one end, we're going to have to consider some other cases. So essentially what this will come down to is finding any local extrema and determining if they're also absolute extrema. So one new method that we'll introduce for this is a new derivative test. We've already seen how we can find local extrema using derivatives. So for instance, if we had a graph or if we had a function, we could look at a sign chart for its first derivative and see that it changes from decreasing to increasing, or changes from increasing to decreasing. Either of those types of behaviors would mean that we have either a local minimum or local maximum occurring. So with that sign chart for the first derivative, we would identify this point by finding that as a point where the first derivative is either equal to 0 or undefined. Let's see, we don't know that's happening at 0. So we would have a point on either graph where the first derivative is equal to 0, and then we'd look to see that the sign for that first derivative changes. But if what we're saying is the first derivative is equal to 0, then that means the tangent line for the function at that point would be a horizontal line, meaning it has a slope of 0. So at these points, we know that our first derivative is equal to 0. So the tangent line has a slope of 0. The other thing that we could identify is the concavity of our function. So in the case where we have a local minimum, we can see that this function is concave up. And in the case where we have a local maximum, we see that our graph is concave down. So in the first case, what essentially we have going on is, again, our first derivative is equal to 0, and our function is concave up, meaning the second derivative should be greater than 0. For a case where we have a local maximum, we would have the first derivative equal to 0, and the second derivative being less than 0. So this gives us a new method for classifying local extrema using both the first and second derivatives, and gives us the advantage of not having to construct sign charts to look at that change in behavior of the function. So formalizing this process a little bit, we can set up our second derivative test. So we would first need to verify that our function is continuous on that given interval. We would need to find all critical values, which again are values where our first derivative is either equal to 0 or undefined. We would evaluate f prime and f double prime at each of those critical values. And then we would have 3 different cases to consider. So if f prime of c is equal to 0, and f double prime of c is something greater than 0. So we know the first derivative is equal to 0. The second derivative is greater than 0, so our function is concave up. Then c has to be a local minimum. If f prime of c, so the first derivative evaluated at c, is equal to 0, and the second derivative evaluated at c is something less than 0, then we have a function that's concave down, meaning c is a local maximum. So just by finding critical values and then evaluating the second derivative of those points, we can identify local maxima or minima. But our third case, would be in a situation where f double prime of c, so the second derivative, evaluated at c is equal to 0. Unfortunately, in that case, the second derivative test is inconclusive. So inconclusive meaning we don't know whether we have a maximum or minimum. The test doesn't give us any useful information. So in a case where the second derivative test is inconclusive, then what we'll do is go back to the first derivative test, where we look at sign charts to identify local extrema. So the second derivative test is an alternative to the first derivative, doesn't require the construction of sign charts, but the first derivative is still our backup in this third case where the second derivative test fails. The other thing that we'll need to consider is the end behavior of our graph. So whether we use the first derivative test or second derivative test, all we're doing is identifying any local extrema. The other thing we'll need to consider is the limit of our function as x approaches both positive and negative infinity. So if we evaluate the limit and we end up getting positive infinity as a result, and in this case it means on either end, so as x goes to either positive or negative infinity, if either of those ends up being infinity, then we have no absolute maximum. Because what that infinity means is that our function is just increasing without bound to positive infinity. So there can be no point, no function value that's larger than any other. The other case would be as if we get negative infinity for either of those limits, and in that case there would be no absolute minimum. Because again, what that means is that either on the left or right end, our function is just plummeting to negative infinity, so there can't be any particular function value that's smaller than all the others. So we need to identify local extrema using one of the derivative tests, and then also consider the end behavior to see what's happening at the extremes for our function.